Summer 1972, a pro-stock pit area at US 30 Dragway. The cars lined up that weekend all shared the same basic recipe, same class weight brake, same body style regulations, same suspension architecture. NHRA's rulebook had approved for the category. On paper, chassis-wise, there was almost nothing separating one pro-stock Camaro from the next. Bill Jenkins' car left the line and did something that made a row of crew chiefs standing along the guardrail stop talking mid-sentence. It was not wheel spin. It was not a hole shot. It was the way the car settled, planted, and hooked, transferring weight to the rear tires with a smoothness that looked almost gentle compared to the violent, chattering launches coming out of nearly every other car in the field. Where competitors' cars fought for traction through the first 60 feet, Jenkins' car simply left clean, controlled, and gone. A rival team owner walked over to Jenkins' pit stall between rounds that weekend and asked, half joking and half genuinely desperate, what suspension parts he was running that nobody else had access to. Jenkins reportedly told him, with the dry, blunt honesty that earned him the nickname the Grump, that he was running the exact same parts as everybody else in the class. The owner didn't believe him. Neither did most of the garage area. Word of the exchange spread through the pit lanes over the following hour the way these things always do at a national event. And by the next round, half the competitors in the class were quietly recalculating their own setups, unsure exactly what they were even looking for. NHRA technical inspectors measured that chassis more than once that season. They checked wheelbase. Legal. They checked suspension mounting points against the approved specification. Legal. They checked ride height and ground clearance. Legal, every dimension on the sheet came back clean, and every single time, Jenkins' car kept hooking off the line in a way nobody else's car could replicate on the exact same tires, the exact same track, the exact same class rules. One inspector who had been checking pro-stock chassis setups since the class's earliest seasons later admitted that he crawled underneath Jenkins' car with a flashlight that weekend, half convinced he would finally find whatever it was everyone kept whispering about. He found nothing but clean, legal, properly welded tubing exactly where the diagram said it should be. Whatever Jenkins was doing was not sitting in any single component an inspector could point a flashlight at. It was sitting somewhere in how those components actually behaved together the instant real force hit them, and no static inspection would ever be built to catch that. Here's the part that should genuinely bother you. What that rival team owner saw in the pit area that weekend was not even the most sophisticated thing Bill Jenkins ever did to a pro-stock chassis. Stay with me, because in the next 30 minutes, I'm going to take you inside the mind of the man they called the Grump, and I'm going to show you 5 chassis and suspension modifications Bill Jenkins built into his pro-stock combinations, modifications so precisely built around the exact wording of NHRA's rulebook that technical inspectors could put the entire car on a set of scales and a measuring jig, check every number the rulebook named, and still never find a single dimension they could legally call a violation. I'm going to show you the actual physics of weight transfer, the actual mechanics of suspension geometry, the actual engineering behind each one. Not pit lane legend, not folklore. The real reasons Jenkins' cars could put power to the pavement in a way that identical hardware, bolted to identical cars, in the hands of other crews, simply could not replicate. By the end, you will understand why a chassis inspection built entirely around static measurement was never going to be enough to catch what one man was doing the instant that chassis actually started moving. And I'm going to make you a promise right now. By the time this video ends, you will understand exactly why NHRA officials spent years suspecting Jenkins was doing something to that chassis they could not legally prove, and why, by the time they finally wrote language specific enough to close what he had found, he had already moved 3 steps further down the same road. The most uncomfortable part of that promise. Every single one of these modifications was legal on the day it raced. NHRA never once found a rule Jenkins had actually broken. Let's go back to where this story actually begins. Not with the suspension's moving parts, but with a basic assumption about frame rigidity that every other pro-stock team in the country had simply stopped questioning. The frame that was engineered to flex, not fight NHRA's pro-stock rulebook regulated chassis construction with real precision. Frame rail material, minimum tubing dimensions, mandatory roll cage specifications, all measured against a strict safety-driven baseline, all locked to prevent teams from building something dangerously light or dangerously unconventional. Every crew chief in the class read that rule and understood it correctly. The frame's basic construction parameters were frozen in place. It was the kind of rule built primarily around driver safety, and safety rules tend to get written with a specific hazard in mind, a frame collapsing, a roll cage failing, rather than with any thought toward how a perfectly safe, perfectly legal frame might still behave differently from another perfectly safe, perfectly legal frame once real racing forces were applied to it. What the rule did not regulate with anywhere near the same precision was how that frame was engineered to behave dynamically once real launch forces were actually applied to it. This distinction is the whole story, and it is worth sitting with for a moment. Most builders in this era treated chassis rigidity as an unambiguous virtue. The stiffer the better, on the assumption that a completely rigid frame transmitted engine power to the tires with the least possible waste. Jenkins looked at that same assumption and asked a more specific question. What if a small, precisely engineered amount of controlled flex in the right locations actually helped load the rear tires more effectively during the violent first fraction of a second off the line, rather than fighting against it? There is a reason nobody else in the class had seriously questioned the rigidity is always better assumption. And it is worth understanding before we get to what Jenkins actually did differently. Rigidity is easy to measure and easy to defend to a customer or a sponsor. A stiffer frame sounds on its face like a better frame, the same way a bigger engine sounds like a faster engine even when the details of tuning matter far more than raw displacement. Chasing controlled flex instead required a builder to trust a counterintuitive idea, that sometimes giving a structure a small amount of purposeful give produces a better outcome than making it as unyielding as physically possible. And trusting a counterintuitive idea against an entire garage area's conventional wisdom takes a specific kind of stubbornness most competitors simply did not have. Think about the difference between jumping off a rigid concrete platform and jumping off a diving board. The rigid platform gives you nothing back. All the energy of your jump has to come purely from your own legs. The diving board flexes under your weight first, then springs back, adding stored energy to your jump that a rigid platform simply could not contribute. A completely rigid Pro Stock chassis was behaving like that concrete platform under launch, transmitting weight transfer forces instantly and abruptly, in a way that could actually unsettle rear tire grip in that critical first instant rather than helping it. He worked with frame rail wall thickness and cross-bracing placement, always within NHRA's legal material and dimensional minimums, to engineer a small, specific amount of controlled flex into the rear portion of the chassis, timed to work with the violent weight transfer of a hard launch rather than against it. The frame would load under initial torque, flex in a precisely calculated way that helped settle weight onto the rear tires progressively instead of instantly, then return to its normal geometry as the car left the line. Milliseconds of engineered movement invisible to the eye, but very much present in how the tires actually behaved against the track surface. NHRA inspectors measured tubing diameter and wall thickness. Every dimension matched or exceeded the legal minimum. They checked cross-bracing placement against the mandatory safety points. Everyone was present and correct. Nothing in the rule book described how a frame needed to behave dynamically under load, because nobody writing that rule had imagined that two frames meeting identical static dimensional requirements could behave completely differently the instant real launch forces hit them. NHRA eventually moved towards stricter chassis rigidity testing protocols, closing the exact gap Jenkins had found. But the launches from before that testing existed had already gone into the record books, permanent. What made this particular secret so difficult for rival crews to reverse engineer was that the difference lived entirely in behavior nobody could see with the naked eye. A crew could put Jenkins' frame rail specs side by side with their own and find numbers that matched or nearly matched at every measured point. The actual difference, milliseconds of calculated purposeful flex under real launch load, was invisible to any inspection method available at the time. The kind of thing you could only detect by instrumenting the car with strain gauges and high-speed cameras. Technology most teams in this era simply were not applying to something as unglamorous as a frame rail. The four-link geometry that changed its behavior depending on how hard you launched, if the frame flex trick was about engineering the chassis itself to work with weight transfer. The next modification attacked something almost nobody else in the class was thinking about with the same precision: how a four-link rear suspension's instant center, the geometric point that determines how launch forces translate into rear tire loading, actually behaves as it moves through its range of travel rather than at a single static measurement. It is the kind of variable that sounds almost academic described in isolation, and yet governs, more than almost any other single factor, whether a launch translates cleanly into forward motion or gets wasted in wheel hop and lost traction. NHRA's rulebook regulated four-link suspension within a defined category, approving the basic architecture and setting limits on certain mounting locations to keep every team within a similar suspension type. Most crews in the class treated their instant center as something you calculated once, at static ride height, dialed in your bar angles to hit a target number, and considered the job finished. Here is the physics that made that assumption incomplete. A four-link suspension's instant center is not actually fixed. It moves as the suspension compresses and the car's body rotates under launch, and the rate and direction of that movement depends entirely on the specific angles and lengths of the individual links. Two suspensions that share an identical static instant center measurement, taken with the car sitting still in the pits, can behave in completely different ways once the car is actually launching, because their instant centers migrate to different locations as the suspension moves through the exact travel range a hard launch actually uses. Most crews in the class, even good ones, were essentially tuning half the problem, dialing in a number that looked correct on paper and stopped there, because the tools and the theoretical framework to think about instant center migration through a range of motion were simply not part of the standard tuning conversation most shops were having in this era. Jenkins was not working from secret proprietary knowledge unavailable to anyone else. He was working from the same underlying suspension geometry principles every serious chassis builder had access to. The difference was that he actually carried the analysis one step further than everyone else was willing to go. Jenkins calculated and adjusted his link angles and lengths entirely within the mounting points and hardware the rulebook approved to control not just where his instant center sat at static ride height, but how it migrated through the specific range of suspension travel his car experienced during an actual launch. The result was rear tire loading that stayed optimally aggressive through the entire critical window of the launch, rather than being correct for one static moment and drifting away from ideal the instant the car actually started moving. NHRA inspectors measured mounting point locations against the approved specification. Every point matched. They checked link lengths against the legal range. Everyone was within limits. Nothing in the rulebook described how an instant center needed to behave dynamically through a range of suspension travel, because nobody writing that rule had considered that dynamic instant center migration was even a variable separate from the static measurement everyone was already checking. NHRA eventually introduced dynamic geometry testing requirements, closing a gap that had existed purely because officials had been measuring a snapshot of a suspension system that was never actually standing still during the moment that mattered most. Think about the difference between a photograph of a diver mid-dive and watching the entire dive unfold in real time. The photograph can tell you exactly where the diver's body was at one instant, and that information is accurate, useful, and completely insufficient for understanding how the dive actually went. A static instant center measurement was that photograph. Jenkins was the only one in the class studying the entire dive. The wheelie bar adjustment that changed between rounds without touching a sealed component NHRA required suspension hardpoints and geometry to be verified and locked at technical inspection, for reasons every serious racer understood. Officials needed a way to confirm, before a car ever staged, that its chassis matched what would be legal to run for the entire event. A system that could be radically altered between rounds out of view of any inspector threatened the entire premise of a pre-event check. It was on its face a comprehensive rule, one that most competitors assumed left no meaningful daylight for a crew to exploit between the moment a car passed inspection and the moment it actually staged for a run. The rule, as written, locked the core suspension mounting points in hard geometry, the parts an inspector could physically measure against a reference jig. It said far less about wheelie bar height and preload adjustments a crew could make between rounds. Using nothing but standard adjustment points, every wheelie bar of this design already had built into it for ordinary tuning purposes. Every track surface presents a slightly different combination of grip level and track temperature from round to round, sometimes shifting meaningfully between morning qualifying and afternoon eliminations as conditions change. A wheelie bar calibrated perfectly for one grip level can allow slightly too much front-end rise on a higher grip surface, or not enough weight transfer assistance on a lower grip surface, costing precious time in exactly the violent first instant of a launch where a race is so often decided. Most teams set a single wheelie bar height and preload for an entire event, and lived with whatever compromise that produced as conditions shifted around them. Jenkins treated wheelie bar calibration as a variable to be actively managed round by round, reading track conditions with the same seriousness other crew chiefs reserved for tire pressure, and adjusting bar height and spring preload between rounds using nothing but the hardware's standard legal adjustment range. The result was a launch that kept rear weight transfer optimized to the conditions actually present at that specific moment, instead of a setup calibrated once at the start of the day and left to drift out of tune as track conditions evolve. NHRA inspectors checked wheelie bar mounting points at technical inspection and confirmed they matched specification. They had no rule prohibiting standard height, and preload adjustments a crew was already permitted to make as part of ordinary tuning. It took years of watching Jenkins cars post unusually consistent launches across wildly different track conditions before anyone connected the pattern to a discipline most competitors treated as a set-it-and-forget-it afterthought. Consistency, more than raw peak speed, is what actually wins elimination rounds in drag racing, because a bracket or heads-up format built on repeated head-to-head passes punishes a car that launches perfectly on one run and inconsistently on the next far more harshly than it rewards a car that is merely fast once, a crew chief who could deliver the same launch quality round after round. Regardless of whether the track had cooled off between sessions or heated up under an afternoon sun, was not just winning individual races. He was systematically removing the variance that eliminated other teams before their raw speed ever got the chance to matter. The body mounting points that let the chassis twist just enough, the fourth modification, attacked a limitation almost everyone in the class treated as simply fixed by common practice rather than by any specific rule. NHRA regulated body panel dimensions and overall silhouette with real precision, and most teams assumed that mounting the body as rigidly and solidly to the chassis as possible was simply the correct, obvious way to build a car. It was the kind of assumption nobody in the garage area had ever actually tested against an alternative, because rigid body mounting was simply how every stock car and every race car derived from a stock car had always been built. What the rule book regulated tightly was the body's external shape and legal dimensions. It said almost nothing about the specific compliance and mounting hardware connecting that body to the chassis underneath it, treating body attachment as a purely practical detail rather than a performance variable worth writing precise language around. Think about how a runner's shoe is built with a sole that flexes at exactly the point where the foot naturally bends, rather than being molded as one rigid, unyielding block from heel to toe. A completely rigid shoe would fight the runner's natural stride at every step. The engineered flex point lets the shoe work with the body's motion instead of against it. Jenkins applied a similar principle to how his car's body was mounted to the chassis, using specific compliance in the mounting hardware at calculated points to let the body move in a small, controlled way relative to the chassis during the extreme torque of a hard launch, rather than forcing body and chassis to behave as one perfectly rigid unit fighting the same weight transfer forces. The frame itself was already being engineered to work with. The effect worked in concert with the frame flex tuning from Secret 1, allowing the entire car, body and chassis together, to settle into the track surface during launch in a coordinated way that a completely rigid body-to-frame connection simply could not replicate. NHRA inspectors measured the body's external dimensions and silhouette. Every measurement matched the legal template precisely. They had no rules specifying mounting hardware compliance, because nobody writing the body regulations had considered that two bodies meeting an identical external template could be connected to their chassis in meaningfully different ways that affected how the car actually behaved under load. NHRA eventually specified body mounting hardware requirements, closing a gap that had existed purely because the rule had regulated the shape of the part while leaving how it was actually attached almost entirely open. This was, in a real sense, the modification that tied every earlier secret together into a single coherent system. Engineered frame flex meant nothing if the body bolted rigidly on top of it, fought that flex at every mounting point. A dynamically tuned four-link meant less, if the body's mass was not settling in coordination with how the chassis underneath it was actually moving. Jenkins was not stacking 5 isolated tricks on top of each other. He was building one integrated machine, where every piece had been engineered to cooperate with every other piece during the single most violent, most important fraction of a second in the entire run. The setup philosophy NHRA never fully banned at all. We arrive now at the final piece of this story, and I want you to pay close attention to this one, because unlike the first 4, NHRA never managed to fully close this door. Officials tried for years. They tried. But this modification was rooted in something too fundamentally correct, too obviously the direction serious chassis tuning needed to move in, for any rule to cleanly outlaw it without outlawing careful setup work itself. Weight transfer management across an entire launch, from the moment the transbrake releases to the moment the car crosses 60 feet, is one of the hardest things to get right in drag racing, because the forces involved do not behave in a simple, static way. Chassis flex, suspension geometry migration, wheelie bar loading, and tire deflection are all interacting with each other simultaneously, changing from 1/100th of a second to the next, which means a setup tuned as if each component operated in isolation will always be leaving performance on the table somewhere in that chain. Most teams tuned each component of their chassis separately, dialing in suspension geometry on one day, wheelie bar settings on another, treating each piece as its own isolated puzzle to be solved and then left alone. The same way most home mechanics tackle one repair at a time on a car without stepping back to consider how each system actually interacts with every other system underneath the same hood. Jenkins treated the entire chassis, from frame flex characteristics to four-link geometry to wheelie bar calibration to body mounting compliance, as one integrated system, understanding that a change to any single piece would ripple through how every other piece behaved during an actual launch, and tuning the whole combination together rather than one component at a time. NHRA officials studied Jenkins' approach for years, trying repeatedly to write rule language specific enough to restrict integrated chassis tuning without also restricting the basic legitimate suspension setup work every team needed to do to stay competitive. They never fully succeeded because banning holistic chassis tuning would have meant banning setup work itself, and no sanctioning body was willing to do that to an entire class. Instead, integrated chassis tuning slowly became the standard every serious pro stock team eventually adopted, not because a rule forced their hand, but because Jenkins had proven launch after launch, championship after championship, that treating the chassis as one connected system was simply the correct way to build a competitive car. There is something almost fitting about the fact that this last secret was the one that never got banned at all. Every earlier trick in this video eventually met a rule written specifically to close it, a line item added to the NHRA rulebook the following season that named, however indirectly, exactly what Jenkins had already moved past. Integrated chassis philosophy never got that treatment, because by the time officials fully understood what he was doing, half the garage area had already started copying it, and you cannot write a rule outlawing a practice that has quietly become the accepted standard for how the job is supposed to be done. Here is what I want you to sit. With every modification I have described in this video, the engineered frame flex, the dynamic four-link geometry, the round-by-round wheelie bar calibration, the compliant body mounting, the fully integrated setup philosophy. None of them required a laboratory most teams could not access. None of them required an unlimited budget, Every single one of them came from one man treating a chassis every other crew chief in the class considered a solved, static structure. As a dynamic system worth mapping down to the smallest detail, everyone else had decided was not worth the time. Consider for a moment exactly how much discipline that approach actually demanded. Isolated tuning is easy in the sense that it is bounded, one variable, one adjustment, one measurable outcome checked and moved on from. Integrated tuning has no natural stopping point, because a change to wheelie bar preload might shift how the four-links dynamic instance center behaves, which might shift how much the frame flexes under the resulting load, which might shift how the body settles relative to the chassis. An endless chain of interacting variables that most crew chiefs simply lacked the patience or the testing resources to chase all the way down. Look at the pattern running through all five, because it says more about how Jenkins thought than any single trick does on its own. Every one of these modifications lived in a gap between what NHRA's rulebook regulated as a static, measurable object and what actually determined how that object behaved once real, violent, dynamic forces were applied to it in the first 60 feet of an actual run. A chassis rule can freeze a tube diameter, a mounting point location, a body silhouette. It cannot easily freeze the precision with which a genius is willing to engineer how those frozen dimensions actually move and interact once the trans-brake releases, and Jenkins understood that distinction more completely than almost anyone else who ever stood in a pro-stock staging lane. That distinction is also, in a strange way, the most honest explanation for why NHRA could never fully prove what he was doing, even when they strongly suspected something was different. A rulebook built around static measurement will always struggle to catch an advantage that only reveals itself in dynamic motion, in the fractions of a second between a car sitting still on a scale and a car launching at full force down a quarter-mile of asphalt. Bill Jenkins was never working with the largest budget in the class. He earned the nickname the Grump partly from a reputation for blunt, no-nonsense honesty about exactly how much work real speed actually required. The kind of honesty that had little patience for competitors who assumed a stock-appearing chassis was performing identically to every other stock-appearing chassis in the field. What separated him from almost every other builder he raced against for 2 decades was a specific, uncomfortable kind of patience. A willingness to chase precision in places every competitor had already decided were close enough. In the case of the chassis, a structure every rival team treated as a fixed, finished piece of the car. He almost never treated it that way at all. And in the space between what the rules prohibited and what the physics of weight transfer and suspension dynamics actually allowed, Bill Jenkins built chassis setups that let his cars translate identical engine power into more usable traction than every other team in pro stock could manage, with the exact same suspension architecture bolted underneath them. He did not cheat the rulebook. He read it more carefully and understood the physics underneath it more completely than the people who wrote it. That is the thread running through every trick in this video, and honestly through nearly everything Bill Jenkins ever touched across a career that helped define an entire class of racing. Other builders read a rulebook looking for the boundary. Jenkins read it looking for the words the boundary was actually made of, and time after time, championship after championship, those words left more room than anyone else in the staging lanes had ever bothered to notice. Somewhere in a modern pro stock or pro mod pit today, a young crew chief is running strain gauges on a chassis rail or mapping instant center migration through laser measurement systems, treating dynamic chassis behavior as completely ordinary, unremarkable standard practice for building a competitive car. He almost certainly has no idea he is doing something Bill Jenkins figured out with nothing more than a notebook, a set of calipers, and an uncomfortable amount of patience, half a century earlier, in a garage that had none of the tools modern teams take for granted.